Well, hello, amazing people. Welcome to the penultimate episode of this series of organic chemistry, where we've been learning a whole lot of things. I'm sure you've enjoyed it thus far. And on today's episode, we're going to be learning how to name cyclic compounds, taking it from the start, and we move on till we finish. So let's get to see if we can learn a thing or two on this episode. So we begin by defining what the term cyclic compounds mean. Okay, so when we mention the word cyclic, we're simply referring to a type of compound that has carbon atoms joined in a ring. Okay, in a ring kind of structure. It's kind of circular when you look at the structure, and it forms a closed chain. And I have a very good example over here on the screen right now. You can see a closed loop chain structure inside of this shape. There is no point at which you can, get out once you're inside. It forms a closed looped structure. And if you check it out, the carbon atoms are joined in a ring. The carbon atoms are joined in a ring. It forms a closed chain structure and it uses the prefix cyclo. And here is a very good example we have on the screen right now. In the diagram example, each vertex represents the presence of a carbon atom. So what's a vertex? A vertex is simply the point where two lines meet. Okay, so wherever you have two lines meeting, that's a vertex. So we have one over here, we have another one over here, we have one more over here, we have another one here, and finally we have one here. So all these points have carbon atoms C, 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 C. So you can see the carbon atoms joined in a loop chain structure, and there is no point of going out. So that's what a cyclic compound is basically. It has the carbon atoms joined in a ring. It forms a closed chain and it uses the prefix cyclo. We're going to be learning how to name them as we proceed. So this structure on the screen right now is actually a six carbon ring structure, and they are all single bonds. So if I were to name it, I'll count the number of carbon atoms: one, two, three, four, five, six. Now remember, the parent name for six carbon atoms is hex, and since there are only single bonds, it uses the suffix ane, ane. Now when there are cyclo compounds, we need to add the prefix cyclo. So altogether the name becomes cyclohexane. That's the name of the compound. And the parent name, which is cyclo, we add it to the alkane roots, which is hexane, and that's why we ended up with the name cyclohexane. I'm sure you saw how this was carried out. Easy, simple, and straight to the point. So what are the step-by-step procedures you need to take for naming cycloalkanes? First things first, you need to count the carbon atoms in the ring. The carbon atoms in the ring need to be counted. So for example, we have the first structure over here. Remember, I told you that each vertex represents the presence of a carbon atom. So we have one carbon atom here. Let's name it number one. We have another one here, number two, and we have another one here, number three. Three carbon atoms uses the parent name propane. Now, since it's a cyclo compound, we need to add the prefix cyclopropane. That's why we have the name cyclopropane over here. I'm sure you're seeing how everything is being carried out. How about when there are four carbon atoms? One, two, three, four. So we add the prefix cyclo plus the parent name, which is butane. So altogether we have cyclobutane. Same thing goes for this structure over here. We have five carbon atoms, which gives us the parent name pentane. So when we add the prefix cyclo, it becomes cyclopentane. And finally, we have the last one, which has six carbon atoms. When we add the prefix cyclo, it becomes cyclohexane. So that's the basic step-by-step procedure for naming cyclic compounds. Now, somebody might be asking, what if there are substituents present? Well, that brings us to step number two. If there is one substituent present, I repeat, When there is the presence of only one substituent, then you do not need to number it. What do I mean? You do not need to assign, okay, this one should be number one, this one should be number two. No, 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 no. When there is one substituent present, then the carbon atom that carries the substituent automatically becomes number one. So that means the point where the substituent is attached, which is this point, automatically becomes carbon number one. So now that we have that in place, how do we name this now? So let's number the number of carbon atoms that are present. So I have carbon number one here. I can go to the right and say carbon number two, or I can decide to go anti-clockwise and say this should be carbon number two. Either ways is fine. So I have three, four, five, and six. Six carbon atoms gives me the parent name hexane. Now, since there are only single bonds, I know that the name hexane is going to be included in the full name. Now, remember it's a cyclo compound, so we need to add the prefix cyclo. But how about these substituents? You can see it over here. What's the name of this substituent? In my previous video, I showed you some of the alkyl substituents that we have. So the substituent that is present is the CH3 group, and it is called methyl. It's called methyl. So in order to name everything together, we bring everything together. We have methyl plus, since it's a cyclo compound, we have cyclo plus hexane, which is the parent name. So all together, the name of this compound becomes methyl cyclohexane. Easy peasy and straight to the point. I'm sure you can see how all of these steps are being taken to name organic compounds. When there is one substituent present, then the carbon atom that carries that substituent automatically becomes number one. There is no need to go about sharing the numbers. Now, another question you might be asking is, how about when there are two substituents? When there are two substituents, then numbering begins to matter. So here are the rules. Number one, give the lowest possible set of locants. Locants here also means the lowest possible set of positions or numbers. So either you use the word position, numbers, or locants. All of them mean absolutely the same thing. Step number two, if there is a tie, then alphabetical order decides who gets the lower number. Don't get confused. I'm going to show you an example right now. On the screen right now, I have an example. This is a cyclo compound. Not just a cyclo compound, there are some substituents or there are some branches. We have one branch over here and we have another branch over here. So the question becomes, how do we count the carbon atoms? Well, the first rule says gives the lowest possible set of numbers to the carbon atoms that carry the branches. So if I come over here and I say this should be carbon number one, and I come over here and I say this should be carbon number two, and I come over here and I say this should be carbon number three, four, five, and six, it means my branches are going to be on carbon number one and on carbon number three. As you can see, this is carbon number one and carbon number three carrying the branches. How about if I decide to number in the clockwise motion? What will happen? Well, let's check it out. This becomes carbon number one, carbon number two, carbon number three, carbon number four, carbon number five, and carbon number six. I still have my branches to be on carbon number one and on carbon number three. So it's a tie. 1 3 1 3. If I go clockwise, 1 3. If I go anti-clockwise, it is still 1 3. So the question becomes, how do I number? When that's where we get to go for alphabetical order. The name of this guy is called methyl, and the name of this guy is called ethyl. The question becomes, who gets priority in alphabetical order? This guy becomes this guy starts with the letter M and this guy starts with the letter E. In the alphabetical order, E comes before M, so we're going to give priority to this guy. I'm sure you can see how that's being carried out. So in order to number the carbon atoms, it means this one becomes number 1. This becomes number 2, this becomes number 3, this becomes number 4, this becomes number 5, and this becomes number 6. I'm sure you can see how that was carried out. We have 6 carbon atoms, which tells us that the parent name is going to be hexane. Now, since it's a cyclic compound, remember we'll add the prefix cyclohexane. Now, how about the branches? Let's begin to name the branches. Now, we have on carbon number 1, we have ethyl. So in order to name that, we put 1 ethyl, and then on carbon number 3, we have methyl. 1 ethyl, and then we have 3 methyl. We've handled the substituents or the branches. So all of these are the names of the branches. Let's add everything together. So all together we have 1 ethyl, 3 methyl, cyclohexane, 1 ethyl, 3 methyl, cyclohexane. I'm sure you can see how that was done. So you know what to do now when there are two substituents present in a ring. So now, another question or another scenario that may play out is it possible for the ring to become a branch instead of the main structure? My answer to that is an emphatic yes, it is possible. If the ring structure has fewer carbon atoms than a side chain attached to it, then that ring becomes a substituent called cycloalkyl. Let me explain. Let's say a ring structure, a cyclo compound contains 3 carbon atoms, and then a supposed branch contains 4 carbon atoms. What that simply means is that this structure with 4 carbon atoms becomes the parent structure, and this guy, the ring structure with 3 carbon atoms, becomes a branch. Don't worry, we're going to treat an example that shows how this can be done. So here are some key rules for doing the naming for structures when this kind of scenario plays out. First things first is you need to select a parent chain. If the acyclic chain, acyclic here simply means the straight chain. So if the acyclic chain is longer than the ring is a branch or a substituent. So if the ring name keeps its cyclo prefix but changes the ending to "-il". Look at this example. 1 cyclopropyl pentane. What this is simply telling you is that the parent chain is the pentane, and then cyclopropyl is located on carbon number 1 of this pentane structure. I'll show you an example, don't get confused. And then thirdly, number the chain to give the substituent the lowest possible number, similar to alkyl branches. So let's check out an example to buttress what I'm talking about. You can see this example on the screen. Okay, here is the cyclo compound, and then here is the straight chain structure, the acyclic structure. Now my question to you is, which one has more carbon atoms? Well, let's find out. For the cyclo structure, I have 1, 2, 3 carbon atoms. The cyclo has 3 carbon atoms. For the acyclic structure, I have 1, 2, 3, 4, 5, 6 carbon atoms. So for the acyclic structure, there are 6 carbon atoms. So it simply means that the parent structure will become this one and not this one. So therefore, it means I will treat this one as the parent structure, and then this one becomes a branch. So how do I name it? Well, the first thing to do is to get the number of carbon atoms in the parent structure. So I have 1 carbon atom, 2 carbon atoms, 3, 4, 5, 6. 6 carbon atoms means I have the parent name hexane, since it is an alkane, single bonds throughout the structure. Now, this is the branch. Now, when cyclic compounds become the branch, they retain their prefix cyclo, but then their ending changes to an alkyl name. So let me identify what the branch is now. The branch contains three carbon atoms and it is a cyclic structure. So when it is a cyclic structure, we name it cyclo. Now, three carbon atoms. One, two, three. Three carbon atoms in the cyclic structure. That gives us the name propyl. Remember, it's the branch now. So we are using the ending of the name to be "-yl", showing that it is a branch, an alkyl branch. So we have cyclopropyl. Now, what position is it located on? It is attached to the carbon number one. You can see it over here. So in order to identify that, it becomes 1 cyclopropyl. That is the identity of the branch. Now let's add it to the parent name, which is hexane. So altogether, the full name of the compound becomes 1 cyclopropyl hexane. Can you see the steps, or did you see the steps that I took? First things first, I identified the parent chain, identified the branch, and then took the next appropriate steps afterwards. 1 cyclopropyl hexane. All right, let's move on to the next thing we have. The next thing we have is naming cycloalkenes, that is cyclic compounds that contain a double bond. Now, when a cyclic compound contains a double bond, there are key rules you need to follow. The double bond carbons will automatically become carbon number one and carbon number two. Look at this structure over here. There is a double bond. It simply means the carbon atoms carrying the double bond becomes 1 and 2 if you are counting in the clockwise direction. But if you're counting in the anti-clockwise direction, that is like this, it means this will become 1 and 2. That is for cyclo compounds that contain double bonds. I'm sure you can see how that's going on. So the numbering starts at a double bond carbon. That was what we just did. And then we proceed in the direction that gives substituents the lowest number. So for example, let's say there is a substituent here, CH3, just for example. So it means I'm going to start counting in a way that will give this substituent the lowest possible number. So if I start counting from this position over here, 1, 2, 3, it means this substituent will be attached to carbon number 3. But if I started counting from the first carbon atom, 1, 2, 3, 4, 5, 6, this substituent will be on carbon number 6. So that would be the wrong way to count. I want to count it in such a way that the carbon atom that carries this branch gets the lowest possible number. So it will be 1, 2, 3, 4, 5, and 6. So let's check out this example on the screen right now and answer it. We have this structure having 6 carbon atoms, okay? 1, 2, 3, 4, 5, 6. A 6 carbon ring with 1 double bond. So the name simply becomes cyclohexane. The "in" here is to identify the presence of this double bond. So the name is cyclohexane, not cyclohex-1-ene. If it is just one double bond present without any branch, what it simply means is that the position 1 is implied. It is already known that the position of the double bond is on carbon number 1 unless it is needed. I'm sure you can see how this is being carried out, and I'm sure you're getting value for this. If you are, please consider liking, sharing, and subscribing to this channel for more episodes coming your way. Well, how about if there are substituents attached to a cyclo compound that has a double bond? Well, if there are substituents attached, the first thing you need to do, remember, the double bond carries carbon number 1 and carbon number 2. Then we need to proceed in a direction that gives the lowest possible number to the branch. Now, here's what I mean. For example, this structure carries this branch. Let's identify it as the branch. So how are we going to number it? We have a double bond here and we have a branch. So we start numbering from the double bond. The double bond automatically carries 1 and 2. So I have 1, 2, 3. Some people might be thinking, why did I number in that direction? Well, the reason is because I want to number it in such a way that this guy gets the lowest possible number. If I had numbered it the other way around, let's number it the other way around and see. This becomes 1, 2, 3, 4, 5, 6. That means this branch will be on carbon number 6. However, the other way gave this branch carbon number 3. So the correct way to number it will be to start from here. 1, 2, 3, 4, 5, 6. So let's name it. On carbon number 3, I have a branch 3 methyl. I've identified it. 3 methyl. Now I go ahead to add cyclo as the prefix of the parent name of the compound. How many carbon atoms are present? 6. Cyclohex. And since it's an alkene, I add the suffix ene. 3 methyl cyclohexane. I'm sure you can see how that was done. The double bond occupies carbon number 1 and carbon number 2. Easy peasy. So let's move on to the next set of compounds we have, which is cycloalkynes. Now, cycloalkynes are very rare, but in cases where you have them, they are simply cyclic compounds that have triple bonds in rings. So let's name this compound that we have on the screen right now. The same rule applies. The carbon atoms that contain the triple bonds automatically get to be carbon number 1 and carbon number 2. So I have 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms present in this compound. 8. 8. 8 carbon atoms gives me the parent name oct. Now, what suffix am I going to add? Since it's an alkyne, I add the suffix yne. This becomes octine. Now, remember, we always add the prefix cyclo. So this becomes cycloalkyl. Time. That becomes the name of the compound. That becomes the name of the compound. Did you get that? I'm sure you did, and I'm sure you enjoyed every bit of this lesson. Next up, which is the final episode in this series of organic chemistry for high school kids, we're going to be looking at cyclic compounds with functional groups. I can't wait to see you in that series. See you there. And up until then, my name's David. God bless you.